this class, we are going to look at how to write the expression for equilibrium constants of reversible reactions. Let's take these questions here. Question says, write the mathematical expression for the equilibrium constants of the following reactions. Write the mathematical expression for the equilibrium constant of the following reactions. And the equation for number 1 says N2O4 gas reversibly gives 2NO2 gas. This is the equation given for the first one. We are asked to write the expression for the equilibrium constant of this equation. Remember, before you can be able to write correctly the expression for equilibrium constant, you must first ensure that the equation given to you is balanced. Looking at the board, you can see that the equation is balanced. I have 2 nitrogen atoms on the left, 2 nitrogen atoms on the right, 4 oxygen atoms on the left, 4 oxygen atoms on the right. The equation is balanced. I can now write the expression. Now, solution. The equilibrium constant, which is KEQ, for this reaction is equal to the concentration of the product. Here, my product is the right-hand side, which is NO2 gas raised to the power of E stoichiometric coefficient, which is 2, divided by the concentration of the reactant, N2O4, raised to the power of E stoichiometric coefficient here, which is what? 1. And this is the answer to the question. Let's quickly look at number 2. Here is the answer to number 1. Equilibrium constant is equal to concentration of the product raised to the power of each number of mole divided by the concentration of the reactant raised to the power of each number of mole. Now let's quickly look at equation number 2. Equation number 2 given to us here says, write the expression for equilibrium constant for this reaction. H2 gas plus I2 gas producing HI gas. Now let's quickly solve this problem. If you look at the equation given to us, you discover that it is not balanced. On the left, we have 2 hydrogen atoms. On the right, we have 1. On the left, we have 2 iodine atoms. On the right, we have 1. So for us to balance this equation, all we need to do is to put 2 here. Everything balances. Now we can write the expression given to us. Now our equilibrium constant expression for this equation becomes the concentration of the product, which is the hydrogen iodide gas, divided by the concentration of the reactants. Here we have 2 reactants. So what we are going to have the concentration bracket twice. Remember, the sign between them is the multiplication sign. So the first one is our hydrogen gas, and the second one is the iodine gas. Each raised to the power of their stoichiometric coefficients. This is 1 for hydrogen, this is 1 for iodine, and here is 2 for hydrogen iodide. And this is the answer to number 2 question. Note this, when writing expression for equilibrium constants, only substances in gaseous states and aqueous states are considered, while those in solid states and liquid states are not considered. Why? Because the assumption goes this way. It is assumed that the concentration of substances in solid or liquid states at equilibrium point is equal to 1. So that is why we don't deem it necessary to bring them into the expression. We are going to solve more examples. Let's solve number 3. Question number 3 says, write expression for the equilibrium constant for this reaction. NO gas producing 1/2 N2 gas plus 1/2 O2 gas. We are asked to write the expression for equilibrium constant for this. First thing you do, check if the equation is balanced. If it is not, you balance it. Looking at it, you can see we have 1 atom of nitrogen on the left. On the right, I have 2 times half, which is 1. Half times 2 here is 1. So I have 1 atom of nitrogen on the right. Half times 2 here is also 1. I have 1 atom of oxygen on the right as well. So the equation is balanced. Now my answer becomes equilibrium constant, which is KEQ, equal to concentration of the products. I have 2 products here, so I'm going to have 2 concentration brackets up, divided by, I have only 1 reactant, so I'm going to have 1 concentration down. So here is my nitrogen gas, here is my oxygen gas, and the reactant is my NO. Now, raise each one to the power of their stoichiometric coefficients. Nitrogen gas, the coefficient here is 1/2. I'll raise to the power of 1/2. Oxygen gas, 1/2. Whereas NO is 1. This is the answer. Remember, all of them are in the gaseous phase. That's why all of them were considered. Quickly look at number 4. There are 7 of them here. So let's quickly look at number 4. Number 4 says, write the expression for the equilibrium constant for this reaction. Fe, that is ions in the solid state, plus steam, that is water in gaseous state, reversibly giving us Fe3O4, that is iron oxide, plus hydrogen gas. This is solid. So we are given this, we are asked to write the expression for the equilibrium constant. Now, first thing to do is to balance the equation. I have 4 oxygen atoms. Okay, let's start with iron. I have 3 iron atoms on the right. I'm going to put 3 here for iron to be balanced. I have 4 oxygen atoms on the right. So I'm going to put 4 by the left hand side so that my oxygen will balance. Now I'm now having 4 times 2, 8 hydrogen atoms on the left. I'll put 4 here so that 4 times 2 will give me 8 hydrogen atoms on the right. Looking at the equation, you can see that the equation is now balanced. We can now solve. Our equilibrium constant is equal to, remember, I told you, only substances in gaseous and aqueous states are considered when writing the expression for equilibrium constant with respect to concentration. So, the equilibrium constant for the above equation is going to be this. Okay. Let me include everything. Then, at the end, you see what will come out. Concentration of iron oxide times the concentration of hydrogen gas divided by the ones of the reactants, concentration of the iron multiplied by the concentration of hydrogen. Each raised to the power of their stoichiometric coefficient. The iron here, the power is 3. The water here, this is water, the power is 4. The hydrogen gas here, the power is 4. And this iron here, the iron oxide, the power is 1. Now, according to the assumption, at equilibrium points, the concentration of solid state substances is assumed to be equal to unity, which is 1. So if this is 1, you will notice that 1 multiplied by concentration of hydrogen gas will give you concentration of hydrogen gas raised to power 4 divided by, this is in solid state as well, and the concentration is assumed to be 1. So 1 raised to the power 3 is still 1. Multiplied by this, we have still raised to the power 4. So this is our answer. In summary, do not consider solid and liquid state substances when writing a equilibrium expression. Let's quickly see the next equation. The fifth equation says we should write the expression for equilibrium constant for calcium carbonate. The solid state producing reversibly calcium oxide plus carbon 4 oxide gas. Let's rush it. If you look at the equation once again, you notice that the equation is already balanced. So let's give the answer. Equilibrium constant for this reaction is equal to concentration of the product. Here, this is a solid substance, while this is gaseous. So we are going to consider only the gas, which is CO2, divided by, on the reactant side, we will have a solid state substance as well, which is 1. As I said, we can decide to include this, we'll call it 1 multiplied by CO2. Let's do that. Because the concentration of solid state substances is assumed to be 1 multiplied by CO2 divided by the 1 of the reactant, and since the reactant is a solid state, it is 1. Our final answer says that equilibrium constant